So let's talk about only on one side, okay, of the actuator. Actually, we have all these kind of spring on both sides. On the other side, we also have another set, okay? So that means the final spring will become even harder because we have another set to share the force. So each crab leg will share only 1/4 of the force. So the 40 being on one side gives 4K0. And out for the whole set, you have two sides. You combine it together. You got the final result will be 8K0. Okay? That's the final result. It's not showing here. Okay, if you consider 2 on both sides, okay, it will become 8K0. Okay? So you consider starting from one cantilever beam, the deflection will become, the spring constant is K0. In out, you have 8 beams connected between the actuator and the center part. So in this case, we will have the spring constant become 8 times of only for the single cantilever beam. 8 times, okay? One side and 2 sides. The other side is not a joint. So we consider only one side, you got 4K0. You consider the other sides, because the two exactly the same spring system support the same force, so they share the force. They share the force, that means the two spring connect seriously, in parallel， 就是它是并联。OK， 有听懂吗？就是你的弹簧串联跟并联，串联的话弹簧变更软，并联弹簧变硬。串联的话呢，同样的力量，它的这个变形量会2倍。OK， 并联的话刚好相反。好，那同样的力量，它会 share 这个力量，所以力量变成1半。好，所以它 spring constant 会变成2倍。OK， 好 ，Yeah， so now you know how to design the spring, okay, by connect them together, okay, seriously or in parallel, okay, okay. Okay, so this is the folded beam. Okay, so this is spring constant for system. Now we consider the damping. Okay. So because it's a dynamic system, so we consider the mass, the damping, and also spring constant. So now you know how to. I think the weight, the mass is easy to count. You just calculate the area, the thickness, and you got the volume, and product with the density. You got the weight or the mass of the system. For the spring, you can consider the cantilever deformation like this. So this is a spring constant. Okay. Now we consider the last one, the damping, the center part. Okay, in the dynamic equation. So the viscous damping actually. So we take a look at the viscous damping. The viscous damping, okay, move now the deformation of the system move the whole system back and forth above the surface. So we consider 2 different cases. The first case is we move only the plate, the top plate, along one direction. Okay, along one direction. So in this case, we call this a flow. We call the coated types flow. When you see the coated types flow, you have a moving plate on the top and a stationary surface on the bottom. So there will be a flow field generated inside this channel. Okay, so with the bottom velocity, flow velocity becomes 0, and the velocity of fluid close to the top surface becomes U0. So you have a velocity on the surface of the flow. So the flow follows the velocity of the plate when the fluid close to the top plate, but on the bottom, the flow speed is 0. So you got a gradient over here, okay, linear gradient. So you have a 0 velocity here, U0 velocity on the top. Is linear relationship. So when you consider the viscous force generated inside the channel, okay, so the viscous tau 0 will be equal mu times U0 over D. You can write it down because it's not in your text. Okay, tau 0 equal to mu times U over D. Okay, U over D is the gradient, the velocity gradient along the vertical direction. Yeah, so the original definition of tau 0 is a mu times a rho u rho y. In the y direction, you have a velocity gradient, rho u rho y. Okay, so then this gradient times the viscosity, you get the viscosity, the shear force from the viscosity. Okay, so from the viscosity, now we want to develop the damping coefficient. How to do that? Okay, because the total friction force from the viscosity will be Fb equal to the total area, surface area, times tau 0. Tau 0 is the friction force from the fluid, right? Okay. Fb equal to A times tau 0. Okay. And remember in the dynamic equation, the center part, the friction force generated, friction generated force will be equal to your damping. That's your damping force. So the damping force will be the other equation, B times your the distance derivative to time, the first derivative to time, B times dx dt. X means your position, T means the time, okay? And this part, and then B, this part will be approximately similar to B times U0. U0 is the moving speed of your plate, okay? So now we equate this one and this one together and plug in tau 0 into here. And out, you can find out the damping coefficient will be proportional to your viscosity times the surface area over the distance. So that means if we want to give a high damping, a lot of friction, you need to consider you can use a very viscous fluid. For example, currently we have like a gas, air between these two plates, but we change the air into water. The viscosity will be increased like 100 times, even 1,000 times. So you can have a lot of damping as well. So you change it from air into water. So we change the damping. Another way to change the damping is by increase the surface area. Okay, you change the top surface area. You also got a lot of damping. And if you reduce the distance between them, you reduce the damping here. Okay, so this is the equation here. So, so now we consider not only the damping, but also the other two parameters together, like spring and your mass together. So we got a factor we call the quality factor. Remember, we mentioned it before. The quality factor means on the top we have the mass times frequency response. On the bottom we have the damping coefficient. So you plug in omega 0 equal to square n over k over m, n over k, sorry, k over m. So you end up, you got the top become the square nk, the mass and the spring constant on the top, and on the bottom you have a damping coefficient. So the quality factor means the product of mk. That means n represents your inertia, and the k represents your spring potential. Okay, so you have two kinds of energy. One is your kinetic energy, 动能. K means spring constant. That means it's your potential energy, 位能. So the product of your kinetic energy and the potential energy, that means the total energy you store inside the system. Okay. So this total energy stored inside the system compared with the consumption of the energy, we call the damping coefficient on the bottom. So if you have a high quality factor, that means in this system you have a very high value of mk product. That means you have a very high value of your total energy, including kinetic energy and your potential energy. Together, you have a lot of energy. And if this value is high, that means you have a large stored kinetic or potential energy, then the friction consumption. So the system will become more on the damped system. On the damped system means the system can vibrate all the time without a stop. Okay, because your friction is small. This kind of system also is what we call a high quality system, high Q system. High quality means the consumption of energy inside the system is minimized. So all the energy generated inside the system will remain changing from kinetic to potential, potential to kinetic all the time without not much consumption. Okay, so this system we call the high quality system. 我再讲一次用中文，因为是比较难懂。这个 quality factor 的品质函数，基本上呢，它上面呢是 inertia， 就是你的这个动能 ，OK， 跟位能，好，你可以把它看成这样子。好，跟下面是你的摩擦的这个比较，摩擦是消耗能量的，动能位能是原来存在系统里面的能量，所以品质函数高的话呢，也就是说你现在存在里面的系统的能量呢，不容易被消耗掉。不容易被消耗掉的意思就是你的动能，对不对？一开始给它一个力量，它会动作，这动能，然后被 spring 压缩变成位能，动能位能，动能位能，这样转换的时候是很完美的，没有消耗。也就是说，你的系统会一直动，不会停下来。系统会停下来的原因是因为你有 friction 消耗。所以在一个高品质函数的系统的话，基本上呢，这个值会很大 ，Q 会很大，也就是说你的动能位能的乘积会比你这个摩擦消耗的这个部分呢，好，比值会大很多 ，OK。反之，一个 low quality factor 的这个系统呢，它下面会很大，就是它的 friction 会很高，会很快的消耗掉你动能位能产生出来的能量，所以很快系统动就停下来了 ，OK。所以看我们要怎么设计。我们前面讲过，如果你是 final project 选陀螺仪的话，你就要考虑需要个 high quality factor 的一个系统，因为它的 operation 是在振动的情况下 operation， 不需要它停下来，不需要它一直加能量让它维持这样的动作 ，OK？ 因为它是这样动的时候，你有科氏力旋转的时候，它会有一个 torque， 那 torque 会让它产生一个另外一个方向的运动，所以它可以量得出那个运动的量，从那个运动量可以量出它的旋转量。所以这个 operation 一直要 keep， 它是一直 vibration 的。这种情况的时候，你就要一个 high Q 的系统。反之，如果你只是一个加速龟，我只是让它动一下就停住的话，你的 quality factor 不见得要很高，要看哈。那这样的情况的时候呢，你可能要设计它变成 critical damping 的系统，所以它本身不要一直没晃动，它到一个定点的时候就停在那个地方，你就可以做量测了。这是不同的运用的方法，哦，这个要特别注意。And talking about the quality factor, the importance of quality factors depends on the design of your sensor. If you are considering to design a gyroscope, okay, for a gyroscope, the operation is always moving back and forth, okay? So you don't want the gyroscope to stop. If you have a high damping coefficient, the friction force will make the system stop quite quickly. So in that case, you need to input a lot of energy to sustain the vibration or the back and forth movement. Okay? But for accelerometer, sometimes we want the sensor move into the right direction and stop over there without vibration. So in this case, we need to increase the damping coefficient until the system becomes like a critical system. So it can move down to the position without vibration for your measurement. So different sensors have different criteria for the quality factor. So you need to understand the differences. But now for the lateral moving system, the quality factor will decide by the friction over here. So I give us a very simple equation, okay? But this equation, remember, is for quartet type flow. Quartet type flow means we move the top plate toward one direction without moving back. Only go forward, no go back. Okay? So actually it's different from the real, we call the Stokes type of flow. The Stokes type of situation is we move the plate back and forth. So this one is more similar to our current situation. So you want to, using this equation, apply onto the Stokes type flow, actually it's a little bit different. So you need to do some modification. Okay? So we will consider the quarter type damper will be the quality factor equal to If you plug the B here into this equation, you got the final result like this. Okay. Now, Stokes type damper, you need to consider the parallel connection of three different quality factor here. The quality factor in the quality type, we only consider between the plate and the bottom surface, right? In the quality type, between the plate and the bottom surface. But in Stokes type, not only this position, but you need to also consider from the plate to the top air. You have air on the top. So there's another, damping on the top. And also on the sides. On two plates, you have two sides on the sides. So you can consider bottom, two sides, and the top. Three quality factor together. So these three quality factor is like an imperial connection. You need to add them together. Okay? That means the damping will be increased. Because not only the bottom you have a damping, on the sides, on the top also have a damping, but with some modification. Now you are moving back and forth, not only go one direction. So, so the quality factor will become very complex. Just let you know, I don't want you want to do very long calculation. You just need to understand there's a modification, and you always can find out this equation from the literature. So now we have the finger to ground, finger to infinity, and the finger to finger, finger between finger, the lateral. This is lateral, this is to the bottom, this is to the top. These three quality factor, you add them together. 1 over quality factor, that means a damping. You add all the damping together. You become the final damping. Okay? Okay. So, but because you are moving back and forth, so that you need to do some modification, not only the QCD. The original is QCD, but you need to have some modification because it's going back and forth. Okay, so add them together, become the final damping you have. Okay? So the modified one will be closer to our current situation. Okay. Okay, this is some definition. You can take a look at later. Okay, no problem. Okay, so the dynamic response for laterally driven system, now we can complete the equation. So the equation, as we can remember, you have a second order equation. So you have a mass here, the damping ratio, damping coefficient here, spring constant here. Okay, so the total force, okay, will be equal to your force you provide into the system. The force, if you are currently you are doing the lateral driven. For lateral driven, the force will be a constant force, as we developed earlier. So it's a constant force. So this part, we just adopt the equation, come over here. So it's a constant force. So for constant force, so you can solve this equation easily. Okay. So you can look back to our accelerometer design. Okay. To solve this kind of second order equation, homogeneous equation, got a homogeneous solution for this one. However, for gap closing, it's not easy. For gap closing, you got a nonlinear force over here on right hand side. So you need to solve this equation by using homogeneous solution plus the spatial solution together. These two together. Okay, this is for gap closing. Okay. So after actually, if you want to understand this system is overdamping, underdamping, or critical damping, you just need to verify the value of a b square minus 4 kn. If a b square minus 4 kn smaller than 0, that means it's a overdamping system. If it's larger than 0, it's a underdamped system. Okay. Again, the frequency response is omega equal to square k over m. Okay, so they're similar to before. Okay, so now you can take a look at the equation similar to the equation we developed in the accelerometer. So that means currently we are using this as a actuator, counter actuator. We apply force, so it can move toward the direction and give force to your object. However, you also can use this as a sensor. So when there is a force applied onto the system from the inertial change, okay, the position change. So this kind of phenomena can be used as a sensor as well, okay, and also can be used to measure the force. So yeah, so it depends on your your idea. So it's quite flexible. Any kind of sensor you can consider that two different ways, actuator or sensor. Yeah, so it depends on how you design, yeah, the things. Okay. So we stop here and for a small break. Please turn back the sign-up sheet. Thank you.